And so it begins, our long trek through Wayland. So for the next few whiles, we're going to be implementing the different Wayland protocols that are necessary for our compositor to actually, be functional as a compositor. Today is just the Wayland setup day, which means we get to answer the question, what is Wayland? And why is it so spicy? So last time we hooked up our keyboard inputs to control things within our compositor. We didn't do anything too groundbreaking with them, we just used them to control the background color and then exit out. Since today we'll be cracking into Wayland, let's start by defining it. I'll be keeping this video to just the essentials for following along with Breezy, but if you'd like to dig deeper into Wayland, I've also thrown together a pretty solid article over on the dev site, and more are on their way. So, put simply, Wayland is just a messaging protocol between application clients and a display server. The messages that are sent determine how an application is shown on your screen, and also how the user interacts with it. It's been slowly replacing the ancient X11 windowing system, which, despite its many quirks, has been super reliable given its long history. Wayland, on the other hand, not so much. It requires compositors and applications to both implement a set of protocols in order to communicate, and those implementations tend to have bugs and compatibility issues, especially in the more niche use cases. I'm currently running a Wayland compositor called Sway. If we run a simple Wayland terminal program called foot with the Wayland debug flag enabled, we're actually able to monitor the messages being sent between the two. And this verbose output here is just a small preview to the number of protocols we're going to need to implement in the coming months. Since we're making a compositor, we're going to be implementing the server side of the protocol. The first thing is for our compositor to set up a socket, which is going to eventually allow clients to connect to it. Let's go check in with Past Ben to see how he fared with this. I think it's good. I made a new Wayland file that follows a similar pattern to our graphics seat and input files. It has a similar initialize and cleanup method, which both get called from within our main file. Got our initialization and our cleanup. The initialization method prepares our socket for clients to connect, but at this point it doesn't actually start processing those events just yet. Alright, so the next step is going to be to set up an event loop for processing those incoming events. Wayland server code already provides us with a loop through Wayland display run, so we're just going to make use of that. In past videos, we defined our own event loop that monitored some file descriptors and reacted to their changes. To use Wayland's built-in loop, we're going to need to replace our existing loop and then integrate our old file descriptors into the new approach. Okay, so here is our new event loop, this WL display run method. It replaces our old while loop, which was pretty straightforward. Just said while we're not shutting down, then call this loop iteration function. Our old loop did three things that we need to get out of this new Wayland method. First thing was that it monitored a bunch of file descriptors. Whenever one of them changed, we called an appropriate handle method. And we are doing that here now. So here's our three file descriptors. Whenever one of them changes, we call the appropriate method, which is here. The second thing it did was it called a render method for each iteration of our loop. And we do that now with this schedule render method inside of our graphics code. So basically, if we're not already scheduled, then go ahead and schedule something with Wayland's event loop to call this render method. And then the third thing that our old loop did was it gave us a way to quit out of it. And Wayland does that with this display terminate method. So now when we press super escape, we call that instead of toggling our shutdown flag. So if we take a look at this in action, make sure it all still works, we'll jump over to our virtual terminal, do a fresh build, and do a run. Starts up, and still toggle our colors. And we can still quit out of it. And if we check standard out and standard error, everything still looks healthy. Now, the point of all of this was so that clients could connect. But for that, we're going to need a way to actually launch a client from within our compositor. So to keep things simple, how about we bind it to a hotkey? Maybe use super T to launch a terminal. I got the hotkey ready to launch a program. is just super T, and it launches a program called BZFoot, which is just a symbolic link to the foot terminal program. Don't ask why it's called foot. And that just calls into the spawn child function, which I have defined down here. All this does is it forks the current process and sets this Wayland display environment variable. And this is important because we need to tell which Wayland compositor the child process should connect to. Keep in mind we have two different compositors running on this computer. We've got Sway, which is running on the main virtual terminal here, and then we're running Breezy on a second virtual terminal. So this is important to make sure that our terminal connects to the correct one. So when we start this child program, we have a few different things we had to set up in our Wayland code. The first is to set up a listener for new child connections. And that's just up here. Basically, whenever something connects, we just print out a message that says, hey, this process ID just connected. Then we also have this cleanup function that we define here, which says, hey, whenever our child exits, we want to reap the process ID from some of the OS tables so that it doesn't become a zombie process. Oh, if we see this in action, jump over to our compositor, run a build, and run our compositor. I'm going to push super T, and nothing appears to happen. Push it again, nothing happens. What gives? So if we check out our standard out file, we can see two things here. It tries to create a client. We actually ran it twice, so it tried to create two clients. And then it immediately reaps those clients. So those clients are immediately crashing and they need to be cleaned up. So let's try to figure out why that is. Do you remember the Wayland display environment variable we set when we start the process? So we can actually run this program and tell it to connect to Breezy from within Sway, and then Sway will actually let us see a bit more in the output. So to do that, first we have to start Breezy, which I'm just going to do here. Now we can jump back to Sway, head over to a normal terminal, and then run our program. So the Wayland debug flag prints out the messages that are sent between the client and the server. The Wayland display tells it which compositor to connect to. In this case, Wayland 0 corresponds to Breezy. Then we've got our application. So if we run this, we do see that, yes, it crashes, and it crashes with the error that there's no compositor. And the reason for that is that we haven't actually implemented any of our Wayland protocols yet. So you can see here in the messages that our client is sending to our compositor, hey, give me the registry, and the registry contains all of the globals that are registered within Wayland. And it sees that we don't have this compositor global, so it doesn't know what to do. I really want to see this application run without immediately crashing. So what I'm going to try to do is implement a few skeleton protocols, a few skeleton handlers, just to see if I can get it to run. And hopefully that doesn't go down too deep of a rabbit hole here. When I say skeleton handler, I was planning to just stub out the request handlers without actually doing anything in them. So my thinking at the time was, hey, maybe if the server never sends the client any messages, the client would just sit there, awkwardly staring back, waiting for a response. I mean, that's what I'd do. But there's a flaw in that plan, which is that both the built-in display and registry objects do actually send messages. And that's not something I know how to turn off, considering how essential they are to our compositor's existence. So given that newfound knowledge, let's go make fun of past Ben and his naivety. Well, as future Ben has probably already told you, this did not work. So I added constructors and request handler stubs to about 6 different object types. But even with those, if we jump over and try to run this, foot still crashes. So another thing I tried to do was run foot against Sway, and that would allow me to record which requests the client sends to the server. And that would hopefully give me some kind of indication as to which APIs, which protocols I actually have to implement to get it to work. But there's about 70, and that's not counting the events that the server needs to send back to the client. Oh, In other words, it ain't happening today. But we don't give up quite that easily here. I think I can create a minimal client that only connects to the Wayland socket and does literally nothing else. So let me go give that a shot. And I'm also planning to make a few compositor changes so that we can actually visualize that client somehow on the screen. But yeah, we'll see how that goes. If we tried to go through Wayland's protocol to properly render a client, that would take a massive amount of effort that unfortunately we just don't have time for today. But doing it improperly is much quicker. We should just need to define some OpenGL buffer objects to represent our application. This can be shown on the screen as a rectangle that's just made up of two triangles. And the size and position don't really matter since they're just representative. Then to render the client application, we just need to create some basic shaders that define how to render those buffer objects, load those shaders into an OpenGL program, and then execute that program from within our render loop. Aha, success! So Super T launches a new application, Super Q quits the applications. And if we jump over and take a look at our code, we track a list of all of our connected clients on our main Breezy object. Whenever a client connects, we go ahead and add them to that object. And similarly, whenever a client disconnects, we get rid of them. Each of these client objects stores the coordinates and colors for each of our application windows. These get initialized when the application connects. And if we look to see what that looks like, here are those colors and coordinates that we're using. And then here is how we create them and store them inside of OpenGL. The OpenGL objects are read and understood by these OpenGL shaders that we've written. If you're curious about any of the OpenGL stuff, there's a few OpenGL pages that I wrote that are available on the notes website that you can check out, go into much more detail. And the last two steps. So when we initialize our OpenGL code, we create a shader program which loads and compiles these two shaders. And then down in our render method, we iterate over each of our clients, load that shader program, and render them as triangles. So to create the test client, I ended up splitting our Breezy project into two main pieces. There's the compositor, which has all the code we've been working in, and then the test client, which is just a simple main.c file. And it's pretty straightforward. This is the whole thing. All it does is it connects to our socket, and then it runs this event loop, which just sleeps for a second and does that on repeat until it receives a sigterm. And this new module in here required some shuffling around of our Meson build files. Our top level one now that defines the project and compiler flags. This now has two subdirectories, one for our compositor and one for our test client. And that also changes our build directory up a bit for where we actually find the executables. Now, when we run all this, voila, arbitrary rectangles. And we're also able to change our background color like we added last time. All right, I think that's a pretty good spot to end this video. Next time, we're going to look into getting some of these protocols actually implemented and hopefully get a desktop background in place. If you want to dig deeper into any of these code changes, there's a PR that I've linked down below in the description, so feel free to check that out. Hope you enjoyed the video, and I'll catch you in the next one.